Welcome back to another video. This is chapter 8. We're going to do the quiz walkthrough. So for question 1, in the following reaction, how many moles of C would be produced assuming stoichiometric quantities of reactants are present? So this question is testing if you really know the word stoichiometric. And stoichiometric means the quantities that are asked for in the reaction. So here we've got 3, 2, and then there's a 1 here that's implied. So how many moles of C would be produced assuming stoichiometric quantities of reactants? This means that this is asking for 3 moles of A, 2 moles of B, and it's saying that that will produce 1 mole of C. So the correct answer for this problem is this first one, which will be different on your quiz because they're scrambled, but 1 mole of C is the stoichiometric quantity of product that will be produced. For question 2, we're asked coefficients in chemical reactions are in what units? In our chemical reactions, as we saw in the previous problem, the stoichiometric quantities were in units of moles. So our stoichiometric quantities are in units of moles. Really just testing if you know the nomenclature here, the verbiage that we use to describe chemical reactions. So for question 3, it says consider the following balanced chemical reaction. And that's honestly very important. You should always be checking to see if your chemical reactions are balanced, if you need to balance them, and then if you do need to balance them, then balance them. But it's asking us how many moles of O2 are required to produce 60 moles of H2O. So looking again at our reaction, our stoichiometric quantities are these coefficients, so 43, 2, 30, and 28. So we're asked how many moles of O2 are required to produce 60 moles of H2O. So if we look at this reaction, these stoichiometric quantities are already in units of moles. So if this is 30 moles of H2O, then the quantity of oxygen that's required, because we want to go from 30 to 60, we just have to multiply by 2, right? Because 30 times 2 is 60. So we'll take our stoichiometric quantity of oxygen. So if 43 moles of O2 will give us 30 moles of H2O, then we multiply that by 2 to get 86 moles of O2. So if we have 86 moles of O2, assuming that we have enough of the other reactants, then we can produce 60 moles of H2O. So 86 is the correct answer there. For question 4, we're asked, in a balanced chemical reaction, you can tell what the limiting reagent will be by the mass alone. So this is testing your knowledge of chemical reactions, but also the idea that we need to convert everything from grams, which is mass. So if we have the masses, what's actually most important is the number of moles. So if you were to look at the periodic table, the elements all have very different atomic masses. And those atomic masses mean that for some molecules, even though we'll have a lot of mass, we'll actually have fewer moles. So let me do an example here. Okay, so I went and grabbed a periodic table, as you'll hear popped in, see here that popped in. So let's use something that has a mass, a really high atomic mass. So let's say gold. Gold has an atomic mass on this periodic table of 196.97. And that's grams per mole. Mochi here is trying to drink my coffee. He got 1 lick earlier and it made him go crazy. So grams per mole of gold. And let's compare that to carbon. So carbon has an atomic mass of 12.01 grams per mole. Carbon, no, Mochi, you cannot lay there. Probably bump the camera. So if we had 1 gram, let's do more than that. Let's do 100 grams of each of these. So if we have 100 grams of gold, and we have 100 grams of carbon. And let's say for whatever reason that gold and carbon will react, and let's just say it's Au plus carbon, just to make this really simple, goes to AuC, which is totally ridiculous reaction, but just for the sake of this, which of these is going to be the limiting reagent if we have 100 grams of each? So if we were to look at this and say, you know, as this statement says in this question, in a balanced chemical reaction, you can tell what the limiting reagent will be by the mass alone. So if we were able to tell by the mass alone which one we're going to run out of first, because that's what our limiting reagent is, then we'd say, oh, well, we have the same amount of carbon and we have the same amount of gold. But this is like from the lecture, comparing large nails to small nails. So if we have 12 large nails, those nails are going to weigh more than 12 small nails. So the mass here is not the number of atoms, it's the mass of all of those atoms together. So let's convert this and you'll see what I mean. So we're going to divide by our atomic mass, 196.97 grams of gold, divided by, or well, 1 mole divided by, so 1 mole of gold divided by 196.97. And then we're also going to do 1 mole of carbon, and that's going to be 12.01 grams of carbon. So 12.01 grams of carbon is 1 mole. I got my calculator here. So if we do 100 divided by 196.97, then we're going to get 0.507. I'm going to use, correct sig figs here. This will give us 0.508 moles of gold. And then if we do 100 divided by 12.01, this is 8.32, again, correct sig figs, 8.33 moles of carbon. So we actually have far, far more carbon atoms than we do gold atoms, right? So we have half a mole of gold, we have 8.3 moles of carbon. So our limiting reagent here would be gold. So to go back and answer this original question, after this long aside, the limiting reagent is the one that we run out of first, and we cannot use mass alone. So the answer here would be false. Because if we were to use mass alone, we're ignoring the fact that atoms have different masses, and therefore we can't use them to determine how many, we can't use the mass alone to determine how many of each atom we have. So for question 5, the limiting reagent is a reactant that has more than enough present. So again, true or false? Now in the previous question, we already sort of had this concept baked in, but just to do a little bit of recap here, let's say that we want to make hot dogs, right? So the one that we're going to run out of first, let's say we have, well, if you buy hot dogs, right, you're going to get, 6 or 12 hot dogs? Let's say it's 6 hot dogs. So you have 6 hot dogs, and then you have 8 buns, because you only bought 1 package of each, and of course they don't come in quantities that work well together. So for any hot dog, any plain hot dog, we're going to need 1 hot dog, and then just to mirror how we do chemical reactions, I'm going to leave off the 1. So a hot dog plus a bun equals a plain hot dog. Okay. So if we look at this, we realize that our hot dog and our bun combine at a 1-to-1 ratio. So if we were to calculate how many plain hot dogs we were able to make, to find our limiting reagent, we would say, oh, okay, we start with 6 hot dogs, because that's what we have, and then we get, for every 1 hot dog, we get 1 plain hot dog. This is one of those things where the words sound weird after you say them too many times. So then that'll give us 6 plain hot dogs. And you can probably already see where this is going. You probably already know this from buying and making hot dogs. You need to get weird quantities to make things work out. So this is the same thing. So one bun, for every one bun, we get one plain hot dog. So then with our 8 buns, we'll be able to make 8 plain hot dogs. But you can see that we would run out of our actual hot dogs first before we ran out of buns. So in this case, hot dogs is our limiting reagent. So the limiting reagent is a reactant that has more than enough present is false. The limiting reagent is the reactant that does not have enough present. It's the one that runs out first. Question 6. Finish and balance the following chemical reaction. Which of the following is a product with the correct coefficient? So we need to take a look at this. And again, like in the last quiz, we're going to predict the products here. And we do that by switching our cation and our anions. We swap our cations, leave the anions the same. So if we have calcium here, we're going to use the other anion, so it's with sulfate here, so it's going to be chlorine now, plus silver, and I'm leaving a gap just in case we need a coefficient. And because that was combined with chlorine before, we combine it with sulfate now. Okay, so we've predicted our products. This is a double displacement reaction. Now we need to balance these products. So calcium, as we know from the periodic table, has a 2+ charge, and chlorine from the periodic table has a 1- charge. So we're going to need 2 chlorines to balance the charge on calcium. For silver, we know silver has a 1+ charge, and then sulfate is one of the polyatomic ions, so that's going to be just one that you memorize. That's a 2- charge. So we need 2 silver atoms to balance out the charge on the sulfate. So we'll add a 2 subscript to silver. So once we've balanced each of our compounds, each of our products, now we can go back and we can balance the reaction according to the number of atoms on each side. So if we start with calcium, calcium's balanced. And then I'll move to chlorine because that's attached to the calcium. It's just a systematic way of moving through it. So then chlorine, I have 2 chlorine atoms here. So let's go back over to the left side. We only have 1 chlorine atom there. And so at this point, we can't add any more subscripts because then we would change the formula of our molecules. So we add coefficients. So now I have 2 silver chlorides. So that 2 means I have 2 silver and I have 2 chlorine. So the 2 chlorine now matches between here and here because we added this coefficient. But that means that we have 2 silver here now. So we need to go over to the right side. Oh, and look at that. We have 2 silver on the right side. So just to go back and check, we have 1 calcium, 1 calcium, whoops. 1 calcium, 1 calcium. We have 2 chlorines for our 2 chlorine. We have 2 silvers, and that matches with these 2 silvers. And we have 1 sulfate, which matches with this 1 sulfate. So we have completed and balanced the following reaction. Now we get to pick and see which of the following is a product with the correct coefficient. So as we look through these, you need to pay attention to not only the coefficient, but to the subscript as well. Actually, this one, silver 2 sulfate, these are the same. So that's probably our answer, but just for completeness, let's go back through and look. We can see that this is silver sulfate. Sorry, the name of this is not silver 2 sulfate. I was just saying the number there. We have silver and sulfate again, but this one doesn't have that 2 subscript. So that's not the right one. Calcium sulfate, this one's thrown in there to throw you off because this is asking for the product. So on the left here, these are our reactants. We're looking for products, so we can throw that one out right away. This one, calcium chloride, it's calcium and chlorine are combined together on the product side, but again, we have to make sure we're checking for the coefficients as well. So this one is also wrong. So silver sulfate, with 2 silvers is our correct answer. And part of what you can do when you look at these answers, this is a little shortcut that you could probably take, especially on this problem. This is not balanced, right? The charges don't balance. Sulfate has a 2-, silver has a 1+, so those don't match up. That can't be one of the products. And the same with calcium chloride. This is a 2+, this is a 1-, so that also cannot be one of the answers because it's not a completed ionic compound. And then this was one of the reactants, so it can't possibly be the answer because we're looking for, again, the products. Okay, question 7. Hopefully the formatting on the PC or on a computer was better than it was on my iPad when I screenshot this. But it says, consider the following chemical reaction. We have 3 N2H4 makes 4 NH3 ammonia plus 1 nitrogen. Again, that one coefficient is assumed. So if we have 10.6 grams of this N2H4, how many grams of N2 will be produced? This is again one of those problems where we are looking for multiple things sort of within a problem. So this is really testing whether or not you know how to do stoichiometry, or this process of converting from grams to moles back to grams. So the first thing that we need to do is write down what we have. So we have 10.6 grams N2H4, and then we want to know the number of grams of N2. So the first step in any stoichiometry problem is to get to moles. So we need to go from our grams, let's do a little solution diagram, grams, whoops, N2H4, and then from that we're going to go to moles, N2H4, then there we can use now our reaction, and we can go to moles of N2, and finally to grams of N2. So we need the molecular mass then of the N2H4, so dinitrogen tetrahydrite. So that's going to be, if you remember how to do those, we have nitrogen and we have hydrogen. And so we have the mass, we go up here to the periodic table, should be 14.01. So use 14.01 is the atomic mass of nitrogen times 2 nitrogens. And then for hydrogen, it's 1.01. And we have 4 hydrogens. So we multiply by 4, right? I'm just grabbing those numbers from here, 2 and 4. So then this becomes 28.02 and 4.04. And then we add those together to get our molecular mass, and we'll get 32.06. So this is 32.06 grams per mole of dinitrogen tetrahydride. So that is the first one that we're going to need. And we're also going to need here the molecular mass of our nitrogen, because this is a Brinkelhoff, one of the Brinkelhoff elements. It's a diatomic. So this is going to be nitrogen, and its atomic mass is 14.01. We have to multiply that by 2 because we have 2 nitrogen atoms here. So it'll be 28.02. And since that's the only element in that compound, this is grams per mole of N2. Now that we have those 2 numbers, we can start working over here. So we're going to start with our 10.6 grams dinitrogen tetrahydride, and we're going to use our molecular mass of dinitrogen tetrahydride here to convert it from grams to moles. So this is, we want to get moles, so we'll do 1 mole dinitrogen tetrahydride divided by 32.06 grams of dinitrogen tetrahydride. So that'll give us moles, and then after we get moles of dinitrogen tetrahydride, to convert from moles of dinitrogen tetrahydride to nitrogen, we're going to use our balanced and completed chemical reaction. And we can see that in these stoichiometric quantities, every 3 moles of N2H4 will give us 1 mole of nitrogen. And if you want, you can rewrite this as a conversion factor. So we say 3 moles dinitrogen tetrahydride equals 1 mole nitrogen. Assuming that we have, oh, I guess in here this is a decomposition reaction because we have a single reactant decomposing or breaking apart into 2 other products. So we can use this ratio. We want to convert 2 moles of nitrogen. So we're going to say 1 mole nitrogen for every 3 moles N2H4. And then now we're going to use our molecular mass for this diatomic nitrogen to convert from moles of nitrogen to grams of nitrogen. So again, that's 28.02 grams per mole. So we want grams now on top, so we're going to do 28.02 grams divided by 1 mole N2. And that should give us our final answer. So let's type these into the calculator real quick. And we're going to get 3.09, partly because, well, I'm rounding there because this is asking for 2 decimal places. So when I say a decimal place, this is 1 decimal place, 2 decimal place. That includes zeros. So if this was 12.04, 1 decimal place, 2 decimal places. Decimal places are not related to significant figures. This would be grams of nitrogen. So you would type in then, for this answer, 3.09 grams. Oops, sorry. On these, we leave off the units and we leave off everything else. Just the number goes in there. So this will be 3.09, and that's in grams of nitrogen. Question 8, complete and balance the following synthesis reaction. So here we're given the type of reaction, and it's a synthesis reaction. So we're going to take our 2 reactants and we're going to combine them together to get a single product. So this is giving you a hint as long as you know what a synthesis reaction is. So looking at this, we have gallium and we have oxygen. So our products are going to be some combination of gallium and oxygen, but how many? And we're given some hints here as well. So hint, this is a limiting reagent problem. All right, that's a good hint. Assume that gallium has a 3+ charge in the product. Awesome. So that's going to let us know this is a 3+. And we know that oxygen is a 2-. So you can use the crisscross rule here, and we'll take our 2- and we'll use the 2 without the sign, and we'll take our 3+, and again we're doing that where we're using 3 without the sign. So now when we have 2 galliums, that's 2 times, 3, that equals 6, and then a 3 times a -2 is equal to a -6. So the overall charge contribution from the 2 galliums is 6. The overall charge contribution from the oxygen is -6. So those cancel out because 6 plus a -6 is 0. So we balanced our ionic compound. Let's get rid of some of this. Actually, get rid of all this. Okay, so now we've got our product, but we need to balance this chemical reaction because now we have 2 oxygens here, but we have 3 oxygens over here. And we have 2 galliums here, but we only have a single gallium here. So one of the first things that we can do, and the first thing that we really should do in this problem, is let's balance the oxygen first. Because once we balance the oxygen, we're going to need to rebalance the gallium. So if we have 2 here and we have 3 there, this is where you're looking for the least common multiple. The easiest way to do that is to multiply them by each other. So 2 times 3 is 6. So on either side, we're going to want to end up with 6 total oxygens. So I will, one second, take our oxygen here and we'll multiply, or, oh, come on. We'll give this a coefficient of 3. And then we'll give our gallium oxide a coefficient of 2. Because now 2 times 3, that's 6 oxygens. And then we also have 2 times 3, so we get 6 oxygens. Again, at this point when you're balancing your chemical reaction, you can't change the subscripts, only the coefficients. So now when we balance that, you see we have 2 gallium, or we have a 2 here multiplied by our 2 galliums in our molecular formula, or really our formula unit. So 2 times 2 is 4. So that means we need to have 4 galliums on the left here. So we'll do 4 galliums there. So now to check, right, we have 4 gallium. This 2 times 2 is 4 gallium. 2 times 3 is 6 oxygen. This 2 times this 3, that means we have 6 oxygens there. So we've balanced our chemical reaction. Now, to the second part of this. If you have 5.13 grams of gallium and 5.23 grams of oxygen, how many grams of product is produced? And again, this is a limiting reagent problem. So one of these is going to run out before we've used up all of the other. And in the end, we'll be making less product with one of these than with the other. Or calculating less product. So let's go and get the mass of gallium. I'm just going to swipe up here to the top. Gallium is 69.72. So we can do 69.72 grams per mole of gallium. And we're also going to need oxygen. And remember, this is, again, diatomic oxygen. So we're going to have 2 oxygen atoms for each of these. So it's going to be 16.00 is what that's grams per mole of a single oxygen. So for 2 oxygens, it's going to be 32.00 grams per mole, O2. So we'll be using that one. And now we need to do just some stoichiometry, right? And every time we want to convert from one thing in a chemical reaction to another thing in a chemical reaction, we have to use moles as the bridge. So we've been given that we have 5.13 grams of gallium, and we have 5.23 grams of O2. I need to correct that because it should be grams of O2 in the question stem. I'll go back on the quiz and check those out. So 5.13 grams of gallium. We want to convert this to moles. We're going to do 69.72 grams of gallium is 1 mole of gallium. And then we need to go from moles of gallium to moles of gallium oxide. So for every 4 moles of gallium, we'll get 2 moles of gallium oxide. And that will give us then our moles of gallium oxide. Now to convert the oxygen, or to do the same math with the oxygen, we're going to do, right, we want moles, so it's 1 mole of O2 is 32.00 grams of O2. And then from our balanced chemical reaction, we're going to get 2 moles of gallium-2O3 divided by 3 moles O2. And that will give us, again, moles of gallium oxide, assuming that each is our limiting reagent. So 5.13 divided by 69.72 times 2 divided by 4 is 0.036 and then to do the other one, 5.23, oops, 0.23 divided by 32 times 2 divided by 3 will give us 0.1089. Sorry, if I'm rounding there, it'd be 90. And these are each in moles of gallium oxide. So as we talked about before on this quiz, the limiting reagent is the one that's going to give us the least amount of product because it's going to run out first, right? Just like our hot dog buns. In this case, gallium is our hot dog, and we've got more than enough buns, but not enough hot dogs for them. So we're not quite done there because we want the grams of product produced, which I overlooked a little bit, but 0.036. And again, you want to use as many digits as possible when you do this. So that's our moles, all the numbers from my calculator, moles of gallium oxide. So now we need to convert this from moles of gallium oxide to grams. And so I'm going to do 69.72 times 2, 16.00 times 3, 69.72 times 2 plus 16 times 3 will give us a total of 187.44 grams per mole gallium oxide. So then we're going from moles to grams, so we want grams on the top of this, 187.44 grams gallium oxide, 1 mole gallium oxide. So we'll take our number up there, 0.03697 times 187.44, and we'll get 6.90, right? So we want 2 decimal places, and that's rounded. So we're going to round to that second decimal place. So the number I got in my calculator, I'll write it in red here, is 6.895920786. Most of that doesn't really matter. So I rounded then, because this is a 5, we round up, so this becomes a 10, carry the 1, and this becomes a 9. So 6.90 grams of gallium oxide. Because gallium in this reaction, this was our limiting reagent. So we can't make more if we run out of one thing. So then our answer would be 6.90, no units. Okay. Last question, question 9. Which best describes theoretical yield? So there's a couple different ways that we can do yield. There's the actual yield, there's a theoretical yield. In this case, we're asked about theoretical yield. So is theoretical yield the yield of unreacted reactants? The yield assuming complete reaction? None of these. Or is it the reagent that is in excess? I think the most tempting answers are the first two. But the correct answer here is it's the yield assuming complete reaction. So it's the yield in theory. So in theory, if we had enough of everything, and if everything reacted completely, that is our theoretical yield. It's the maximum that we can get based on the products that we have. The unreacted reactants doesn't have a name. The reagent that is in excess isn't even the limiting reagent, it's the other one, but we're not usually concerned if it's not the limiting reagent, because it's the limiting reagent that tells us what we can and cannot do. Okay, I hope that was helpful. Remember, these are the best ways to study for the exams because these are the questions that I write. And by taking them and trying to take them in the amount of time that I give you gives me a better idea of how much time I should allot for them on the exam as well. Anyways, that's it for this walkthrough, for this answer guide. Again, I hope it was helpful, and I will see you in class.